In this quick video we will cover the basics of the milling 2D drill cycles. Here I have a simple drawing to drill holes in a part. I have represented the hole locations with both points at the drill location, and with circles that represent the drill diameter as well as the location of the holes. Either method can be used, but I prefer the circles as I like to see the representation of the drill diameter. The first step to defining the drill job is to select the holes to be drilled in the order we wish to drill them. Let's start with the 10 holes in a bolt circle and select them in this order. Remember, the machine is going to drill the holes in whatever order we select them in, so it's important that you select them in a logical order. Also notice it does not make any difference which direction the circles are going in, because we are only using the center of the circle. Now we need to select the type of drill operation we want. You can see by the tool tips that we have categories of drill, drill peck, drill tap, boring, and fine boring. I'm going to start off with just a standard drill cycle and select drill. First, let's name this job. Now we select a tool. This opens up our tool library. I'm going to add a new tool. Choose tool type of drill. Name it 3/8 inch drill. And give it a tool number of 3. You can put in D and L correction here if your machine uses them. I also want to select the use type for this tool. This will be a generic drill. But you can see I can select countersink, or reamer, or many other types of tools. Next I will proceed to fill in the dimensions of this particular drill. Some post-processors get tool information from these comment fields as well. Production automation machines can make use of a tool path color command if it is included in this top comment box, and an arc rate command if it is included in this bottom comment box. I will copy a tool path color for this drill from this chart. Then paste it into the top comment box. There is no need for an arc rate because drill bits can't cut arcs, so we leave the second comment box empty. Please note that not all post-processors use these comments, and some post-processors will use them differently than I am using them here. Now we move over to Technology, and select the options we want for this tool. If you take the time to go back to VectorCAM and modify the tool library with any adjustments you made on the machine, then over time you will have a database of tools with settings that work well on your machine, and no manual editing will be needed. Here I'm going to define a feed rate of 10 inches per minute, and a spindle speed of 1000 rpm. Feed retract is normally only used with certain boring cycles, and is not relevant here, so I am just going to set it the same as feed. Now we select the other options we may want. Some of these options are not supported on all CNC machines, so they would have no effect. If you have tool holders defined for the simulation, you can select the tool holder image here under the Holder tab. Now that we have defined our tool, we click OK to save it to the tool library. Then make sure we select the correct tool and click OK to use it in the drill job. You can see the diameter is filled in for us from the tool library. This entry represents the distance from the drawing axis to where we wish to reference all the other drill Z movements from. Normally this is just 0, especially for a router where all Z values specify a distance above the machine table. However, if you wish to work from the surface of the material, or if the axis is at different Z height for other operations, you have a place to make this adjustment here. For this example, since we want Z equals 0 to be at the bottom of the material, and that is where the axis currently is, we will leave it 0. This value here is what will be the distance to the bottom of the drill bit from the reference we gave it up here. There is a wizard to help calculate this here. This wizard is to help you do the calculation, and the settings in here are not stored. To use it, put the material thickness in this box. Please note that this is only needed if you need the calculation to compensate for the material thickness. However, in this case we do not need to do this, because our reference is at 0, which is also at the bottom of the material, so we should leave this 0. You can see that the drill diameter and angle are taken from the tool library, and it calculates the distance to drill for us. This distance is the minimum amount needed to get the drill bit down so its full diameter has drilled to the point we requested. We have an option to put a little extra distance here if we want to make sure the drill gets all the way through. I will add an additional 30 thousandths. When we click OK to the drill wizard, it transfers the number we calculated into this depth field. If you want a dwell at the end of the cycle, you put a check mark in this box and put the dwell time here. Now we move to the Links tab. Notice that the distances given here are also with respect to the reference we gave it back on the Drill tab. Since our reference was 0, we need to specify all distances up from the machine table. This first value is the coordinate to move rapid down to before the drill cycle starts. This is especially helpful if you are drilling hard materials very slowly but need to approach from a high Z height to get over mechanical clamps. I will set it to 0.55, as this leaves 50 thousandths of clearance above the material thickness of 1/2 inch before I start to drill. This next value is the retract height. This is the height the bit will raise up to during the retract part of the cycle. Let's set that to 1 inch to make sure we don't drag across the material. This last number is the clearance height to move to between the drilled holes. For a standard G81 drill cycle you could just make this the same as the retract distance, but on other drilling cycles like G83 deep hole drilling, the retract height is the height the bit returns to after every increment, and the clearance height is used between the holes. On some machines like CNC routers, they actually perform better and run faster by setting all three of these values to the same number, because it is faster to move all the way up to the clearance height and there is no need to stop at the rapid height. I will set this at 2 inches to demonstrate how these heights work. The Technology tab allows us to override the settings in the tool library just for this job. Normally the tool library will be correct, but should a special job require a temporary change, this is where you would change it. When we click OK, our drill job has been added to the jobs list. It's a good idea to view the drawing in 3D to make sure the drill holes start and stop where you expect them to. And we can also simulate the part being machined as well. Now let's generate the program and verify the coordinates, and I will reopen the drill job to show where the Z values end up. You can see right here that we move to the clearance height of 2 inches before each drilled hole. Next we have a movement to the XY location, and then the rapid move down to the rapid height we specified of 0.55 inches. And the drill cycle with a retract distance of 1 inch. And a final depth of -0.1427 inches. Now let's change the job for a router. In links I am going to change all the values to 1 1/2 inches. Now I click OK and it recalculates. And I regenerate my job. First I click on the job window, then Ctrl A. Then hit the delete key. And I simply click NC from jobs to regenerate the program. You can see now that the retract height is 1.5, and because there are no different heights, all we have are the G81 movements. Now let's close the NC window and go over PEC drilling. Again I select the holes in the order I wish to drill them. Now I select Drill PEC. This is pretty much the same as drill, except it has additional parameter for PEC cycles. The main one here is the PEC increment. This is the distance it will advance each part of the drill cycle. This is used for deep hole drilling. Typically the machine would drill down to this level, then move all the way out to the retract height to get the chips out of the hole, then move rapid back to almost where it was, and then drill another increment until the final depth is achieved. If you put a check in PEC drill with high speed, it sends a different command that is a chip breaker cycle. It is similar to deep hole drilling, except it does not retract all the way out of the hole, it only raises up a fixed distance to break the chip, then starts drilling again. Some machines can also just dwell between each increment, and if your machine supports this, then you put the dwell time here. These two values are only used on machines that can support a variable increment. The idea here is that the increment is reduced by dz every cycle until it reaches the minimum increment size. Therefore the deeper you get, the smaller the increments become. Not all machines support all functions, and if your machine does not support the function, then any values entered will simply have no effect. Now I click OK and we have 2 drill jobs. Let's generate the program. You can now see that the G83 deep hole drilling cycle is used, and it has an increment of 1/8 of an inch. Let's change to drill with high speed, and regenerate the program. We now see we get a G87, which is the chip breaker cycle for this machine. Now that our program is complete, we can export it. I am going to load it into the production automation machine control program. Here we can see the location of the drill holes and the effect that the tool path color command has in the visualization. Also notice the drill symbol used the correct drill diameter taken from the tool library. The tool path color along with the tool diameter help make it very clear what is going on in the program. In this example, where the program is drilling and reaming a hole, we can clearly see the 3 separate tools used. Center drill, drill, and reamer. This concludes the drill cycle video. Thank you for watching.